we will start a topic which we can call basics of fluid mechanics. Here we will brush up or recapitulate the fundamental laws of fluid mechanics, particularly those which are very important for practical calculation and engineering practice. So, I will start with fluid. Now, you see that there is some difference between a solid and a fluid, that is why this name is given. And if we like to give some sort of a definition of fluid, one can define it like this, that it is a substance which deforms continuously under the application of shear stress. So, a few things are very important, that it deforms continuously. In a solid, if we have some applied load, we will see that there will be some deformation, but the solid will not deform continuously. Okay. But in case of fluid, if it is subjected to some shear stress, then it will deform continuously. And this particular property, its manifestation is in the form of flow. So, flow of fluid we get due to this property, and that is why this name fluid has come. I will just give one example. Let us say we have got some sort of inclined plane. This is nothing but a solid board, and what we have done, that we have put some sort of water or some liquid here. What we will see, that it will flow like this. Now, what happens if we take this fluid mass, and we know that its weight is acting in this direction. So, it will have, this weight will have two components, and one component will act as shear stress, or that will induce shear stress. The application of shear stress, there will be a continuous flow of the fluid. So, that is what that I have told in the definition, that it deforms continuously under the application of shear stress. So, we can get the property flow or flow of the fluid due to that. So, this is a very important difference with solid, and that is how the fluid is defined. Then there is another very important difference between solid and fluid, that we know that one important characteristic law of a solid body is that Hooke's law. There is some sort of a proportionality between stress and strain. If we go for a fluid, we will see that similar type of law is there, but that is not identical. The stress there in the fluid is proportional to the rate of strain. So, that is another difference between the solid and the fluid. Well, this is not a typical course of fluid mechanics. I will not go on elaborating all these things, but we know what is a fluid. It will deform continuously under the application of shear stress, and also we know that fluid are of, they can be broadly classified into two groups, that is, one is a gas, another is a liquid. And obviously, there are some difference between gas and liquid. So, we will not go into this, because already we have read those things in physics or in some subject of engineering. Now, very quickly we will go through some important properties of fluid, 2-3 important properties of fluid. The first property is viscosity. This is one unique property of fluid which makes it different from a solid, and also it is very important for understanding different fluid flow behavior or different behavior of fluid. Now, in a nutshell, if we want to describe viscosity, it is like that. It is an inherent property of the fluid which tries to resist relative movement between adjacent fluid layers. So, viscosity is the property which resists the relative movement of adjacent fluid layers. That means, if we have two fluid layers, let us say schematically I am showing them like this. Now, let us say one is moving with a velocity v and other I want to move with a velocity v plus dv, then definitely I will face some sort of resistance, and this resistance comes due to a property of the fluid that is known as viscosity. So, if we see bit closely why this occurs, actually there are different reasons for it, and it is not fully explained, but well, broadly one can say a few reasons like this, that there are fluid molecules, let us say, and in this there will be some sort of cohesive force, and if we want to separate it, separate two layers of the fluid, that means if we want to cause some sort of a relative movement between two fluid layers, then obviously this cohesive force will give a resistance. That is one thing. Another thing, well, let us say there are two layers, but two layers are not adjacent. This is one layer which is having number of molecules like this, and this is another layer which is also having number of molecules. Let us say the characteristic velocity of this layer, the average velocity of this layer is v dashed, and let us say this is v double prime. Now, what will happen? The fluid molecules are at random motion. So, due to that random motion, some molecule will move from here, we can call them molecule or fluid particle, sometimes it is called fluid particle. So, that will move from here to here. When it is moving from here to here, then it is carrying some sort of kinetic energy which is due to the velocity v double prime, and that kinetic energy it is imparting here. Whereas, if another particle that moves from the top layer to the bottom layer, that carries some kinetic energy which corresponds to v prime. So, we can see that this velocity influences the movement of the top layer, and the velocity of the top layer that influences the movement of the bottom layer. So, obviously, if it is moving faster, it will try to push it or pull it faster, and if it is moving at a slow rate, it will try to pull back the lower layer. So, that is why we know, or we experience that if we try to cause some sort of a relative velocity between fluid layers, there is some sort of a resistance. So, these are the molecular explanation for the origin of viscosity. Maybe, I mean, this is not a complete explanation. I mean, in physics there could be a better explanation for this, but grossly this explains why there is viscosity. And another thing one can see that I have told there is liquid and gas. In case of liquid, this adhesive force is very strong, and that is mainly responsible for viscosity, whereas in case of gas, the movement, the Brownian motion or whatever it may be, this random movement of the molecule, that is mainly responsible for the viscosity. Well, now we know that if there is two layers, one is moving with a velocity let us say del v, sorry, v plus del v, and then another is moving with a velocity v. So, the relative velocity between these two layers, that is your del v. and let us say this distance is del y. So, we know that between this layer there will be some sort of a shear stress, and the shear stress tau that is given by mu into del v del y, or more precisely in mathematical notation mu du dy. So, this expression is known as Newton's law of viscosity. Newton's law of viscosity. And when we write this equation in this form, so it is almost understood that this mu is constant, and when mu is constant for fluids, those type of fluids are known as Newtonian fluid. Okay. Of course, there could be variation with temperature for Newtonian fluids also, but at a particular temperature mu is not a function of velocity, or it is not a function of the applied force or the history of applied force, like that. So, if these are true, then the fluid is called a Newtonian fluid. So, at a particular temperature we will get constant mu, mu is not dependent on velocity. Now, we will have very large number of fluids, common fluids obeying this property, and they are Newtonian fluid, like air, water, and then number of oils. So, they are all Newtonian fluids. There are non-Newtonian fluids also. So, we can see there are lot of fluid like tomato ketchup, like toothpaste, etc. They behave in a funny manner, not their behavior is not as simple as is given by this particular equation, and they are non-Newtonian fluid. We will not discuss them, and only here it is important to know that this is the law of viscosity or Newton's law of viscosity. From here we can get some important information, like I will give you one example. Let us say we have got a fixed plate. We want to move another plate at the top of this fixed plate, and the gap between them is filled up by some sort of lubricating oil. So, here I want to draw this with some velocity v. I want to draw this particular plate. So, how much effort I have to put, that I can determine from Newton's law of viscosity. How do I determine this? Now, if we see an exaggerated view of this particular phenomenon, or then we will have this is the velocity distribution in the gap. That means, velocity at the fixed wall is 0. This is a very important observation, that if there is a solid surface and on the top of it if some fluid is resting, and then if there is a movement of the fluid, so the fluid can move with any velocity, but just at the interface, that means where the fluid touches the solid surface, there the velocity is 0. Okay. If it is in contact with a stationary solid surface, then the velocity at that point is equal to 0. So, this we called no slip condition. That means, there is no slip between the fluid and the solid. Well, so as this gap is very small, we have taken a linear velocity distribution. So, tau shear stress, that will be equal to mu into du dy. If this difference is delta, so this is equal to mu v by delta. So, this is our shear stress, and if I know what is the area of the plate, AP, area of the plate, then we can calculate force is equal to tau into AP. Sorry, I have not written tau. So, that will be tau into AP. So, tau we have calculated, or tau we can determine from this equation, and then AP is known, we can calculate what is the force required to move this plate. Similar example can be taken like we know journal bearings. In a journal bearing, part of the shaft which is known as journal, that is inside the bearing. Okay. It is like this, and this is the bearing. Okay. And this gap is filled up with lubricating oil. So, if we see from the end, we will have some sort of a view like this, and the shaft is moving, or the journal is moving, and we have got the bearing like this. So, here also, if we know the RPM of the shaft, if we know the gap, then we can calculate what amount of force is required to overcome the resistance. Now, where that effort is going? Where that effort is going? So, it is dissipated in overcoming the viscous resistance. So, obviously, the amount of mechanical energy we are supplying, as energy cannot be destroyed, it is getting transformed into another form of energy which is not recoverable, and it is getting transferred into thermal energy. So, why I am telling this? So, we can also know how much thermal energy or how much heat is generated. So, in the next step, if we have to keep the bearing at a particular temperature, that is important, because unless we do that, the lubricating property of the fluid, that will get destroyed. So, we have to keep the bearing at a particular temperature. So, how much cooling is needed, that also we can calculate from this exercise. So, step by step, one have to first calculate what is shear stress, then what is the force, then what is torque, then torque multiplied by velocity will give us the power, and that is the power which we have to extract, because that power will get converted into thermal dissipation, and we know how much cooling water or whatever it may be is needed. Maybe some heat transfer calculation will also involve in it. Well, so this is the utility of the equation which I have shown here. Okay. So, direct application of this equation. Then I am going to another property of fluid, which is compressible fluid. You see, a solid, we cannot compress a solid, like we may put enough amount of load, but the change in volume of the solid will be very small. So, a solid is practically incompressible. If we give more and more load, the solid may get crushed. So, but change in volume before crushing will not be much. Same thing applies to liquid also. We can put large amount of load, but the change in volume of the liquid is not very high. But in case of gas, it is not true. we know that if we have got a piston cylinder arrangement, we can compress the gas. Okay. We can inflate a balloon by sending gas inside it, and all right, let us not take some other example. Let us say something like a balloon, but with a solid or non-deformable wall. Then we can put more and more gas inside it. Well, we can put a small amount of gas also, we can put larger amount of gas inside it. So, the meaning is that we are able to compress the gas inside this volume. So, that means we can see that there are certain fluid which are incompressible, and all the liquids are taken as incompressible, and there are certain fluid whose density will change. Density may change with pressure, density may change with temperature. In case of liquid also there is change in density with temperature, but that is small. But in case of gas, we will see that there is large amount of change of density. So, then fluids we can again divide them as compressible fluid and incompressible fluid. Just like before we have had classification that Newtonian, non-Newtonian. So, here also we can have compressible and incompressible fluid. I will not elaborate much in this regard. Then let us look slightly into fluid statics. So, in a fluid, if it is stationary, then we can get dP dz, this can be proved, that is equal to minus rho g. Equation of fluid statics. So, dP dz is equal to minus rho g. It is like this. We have got a Cartesian coordinate system x, y, z, and g we have taken in this direction. In that case, this equation is valid, means we have got a particular direction of z and particular direction of g. So, in a stationary fluid we will have this. Then people may ask, well, if the fluid is stationary, then what is dP? dP dx, and what is dP dy? So, the way I have drawn it, I have taken the coordinate system, both these are 0. So, in x direction and in y direction there will not be any variation of pressure, and we will have pressure variation only along the z direction. Or in other word, in a stationary fluid, the plane which are normal to the direction of gravity, they will be isobaric planes, constant pressure plane. Okay. So, from here one can also draw some sort of a conclusion that the constant pressure surfaces will be always normal to the direction of acceleration. Okay. So, that those things I do not have time to discuss, but this is one of the important equation which one have to remember while he is dealing with fluid mechanics or fluid behavior. So, from this equation we can do again a lot of things, means suppose there is any submerged body, we can determine the pressure on the submerged body, and I do not know, maybe this type of equations are dealt in detail when you are doing your ship design or things like that. I do not know, of course, but well, suppose there is some sort of a dam like this, and we want to calculate what is the force on this dam. We can calculate by the application of this equation. And if we do the integration, then we get dP dz is equal to rho g. So, dP is equal to minus rho g dz, and P minus P0, let us say we can have minus rho g, let us take sorry. So, we will have dz, this is dz, and then minus rho g z minus z0. So, one can accordingly determine the pressure. That means, if you know pressure at a particular location, at a particular datum level, that is your P0, if it is known pressure, then you can determine any other pressure at any other point. Well, this is a very simple case where rho remains constant. If rho varies, then also one can determine it. Well, now I will go to the movement of fluid motion, fluid in motion. When a fluid is in motion, then obviously the behavior will be different, but whatever laws of motion are applicable for solid body, they are also applicable for fluid. That means Newton's laws of motion, Newton's law, that will be applicable for fluid. Only thing is that as the fluid is somewhat different from a solid body, so the end expression of these basic physical laws are slightly different. That is what is difference, that is what is the difference between the solid and the fluid, because in a solid what we can do, we can identify the solid. Once we are identifying the solid, we can define its center of gravity or CG, and based on the CG we can define its motion. In case of a fluid, it is not possible, we cannot identify separate identity of different fluid particle. So, fluid is taken as a continuum, and what we do in case of a fluid, instead of tracking a particular fluid particle, we focus our attention on the space, and on the space how the velocity is changing, how the properties are changing, we try to analyze that. So, the end expression of the equations are slightly different. Anyway, if we take any fluid motion, let us say this is any arbitrary duct through which the fluid motion is taking place. The basic equation, the first conservation equation or the basic equation of physics, which we have to first satisfy for this fluid motion, is the conservation of mass. Conservation of mass. Now, conservation of mass, if there is a movement of a solid object, let us say, so the mass of this object is m, so we can simply write m is equal to constant. But here it is slightly different, as I have told. So, we can take any two cross section, let us say this is 1 and this is 2, and we can write rho 1 A 1 V 1 is equal to rho 2 A 2 V 2 for the fluid. That means, rho is the density, A is the area, and V is the velocity. So, this is how we can write the conservation equation, and this equation is known as, also known as continuity equation. Well, then if density is constant, then we can get simply A 1 V 1 is equal to A 2 V 2. Simply we can get this A 1 V 1 is equal to A 2 V 2. Then we can get the momentum equation. Momentum equation, I will not write the expression, because this one can write it depending on the situation, but basically change of momentum is equal to force. What we have got in case of solid mechanics, the same equation will be valid here also. So, let us say the momentum equation let us say we want to analyze the, or we want to do the momentum balance for a fluid flow problem. Let us say the fluid motion that is denoted by this line, which is known as streamline. You see, the movement of a solid body, it is clearly visible or observable. So, we can describe it, means we can describe it by the locus of the CG as the fluid as the solid body moves from point to point. But in case of a fluid, we have to have some different technique. So, if we define it like this, that let us say a fluid particle is moving and number of particles are there, it is moving in a space which is known in the language of fluid mechanics as the flow field. So, in the flow field, if we have instantaneous direction of velocity like this. So, if we have instantaneous directions of velocities and I mean I draw a line in such a manner such that in such a manner, so that the velocity vectors, this line is tangent at every point to the velocity vector, then this line I will call as the streamline. I will explain once again that in a flow field there are motion of fluid particles in different direction. Now, if I draw a line such that at each and every point the velocity of the fluid particle is tangent to that line, then that line will be called a streamline. This concept is important. So, if there is a streamline and let us say there is a fluid particle, fluid body inside the streamline like this, in this streamline like this, and for this we want to do the momentum balance. What should we do? What are the forces we will consider and the momentum change? So, what we can do, say here some sort of pressure will act, here also some sort of pressure will act. So, we can write P, we can write P plus dP, this is one force. Here shear stress, let us say the velocity is in this direction. So, in these two faces shear stress will act, alright, because the other fluid bodies are moving at different velocities, maybe more than this velocity, maybe less than this velocity. So, this shear stress will come and then we can have the weight of this fluid element. So, these are the forces acting on this fluid body and we can take their component in a particular direction and mass of the fluid body into acceleration in that direction could be equated to that force. So, whatever we do in the solid mechanics, I am not writing it completely because our course does not allow that much of time, but this way we can do the momentum analysis or we can write down the momentum equation for a fluid also. All right. Now, from the momentum equation I will come to the energy equation. So, basically the laws of fluid mechanics, they come from this thing. First thing is your conservation of mass, conservation of momentum and conservation of energy. Over and above, we should have second law of thermodynamics satisfied. If we do all these things, then any type of fluid motion we can analyze. It may be complex fluid motion, the analysis may be complex, complicated, difficult, but it is possible. Well, so we go to energy equation. Here I like to remind you, or I like to like you to note that the energy equation which we have studied in thermodynamics, which is the first law of thermodynamics, that is also valid for any fluid motion, and that we can apply. Now, if we see the first law of thermodynamics for steady state, what we have done there, if you remember, that H1 or Hi plus Vi square by 2 plus Gzi plus Q, that is equal to W plus He plus Ve square by 2 plus Gze. So, this equation for steady state, it is valid for any fluid flow. But when we are discussing fluid flow, in most of the fluid flow, we will find number of situations where there is no thermal energy, exchange of thermal energy, no exchange of thermal energy. And we will also find situations where there is no mechanical work done. So, in that cases, the generalized form of energy equation is applicable, but we can get a simpler form of energy equation. So, that simpler form of energy equation in what we get in a large number of fluid flow situation is known as Bernoulli equation. Bernoulli equation, that actually comes from the momentum equation one can derive, but we are not interested in that. I will just write the final form of the Bernoulli equation. Let us say there is a streamline, and on this streamline we have got 2 point, again point 1, point 2. So, we will have Bernoulli equation in this form: P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2, that is equal to constant. So, this is your Z1, this is your Z2, this is Z is equal to 0. That means, we have selected a datum plane or datum line, and then there is in the flow there are number of streamlines. If we have a streamline, so in this streamline we can have 2 point 1 and 2, and we can write this equation. So, along this streamline actually one can write along this streamline P by rho g plus V square by 2 plus Z, sorry, V square by 2g plus Z, that is equal to constant. Now, I have not derived the Bernoulli equation, but it is important to note at which situation Bernoulli equation is valid. For Bernoulli equation, we have got some assumptions. The assumptions are first thing, the flow is steady, with time there is no change. Then the flow is incompressible. For this particular form of Bernoulli equation, we have got incompressible flow, or rho is equal to constant. third assumption is flow is frictionless. Sorry. Flow is frictionless or there is no effect of viscosity. And fourth one, which I am telling from the very beginning, flow along a streamline. All right. So, we have got these four assumptions, and then we can write down Bernoulli equation. If we look into Bernoulli equation, you see there are three terms, and if you see the dimension of these terms, these three terms, then they are having the dimension of length, and this z actually you see this is the height of the point 1 from the datum line. So, they are sometimes called as head, or most often they are called head. Z is called head, and similarly the other terms are also called head, like P1 by rho g, that is known as pressure head, V1 square by 2g, that is known as velocity head or kinetic head, and Z1 is known as the static head. Okay. So, along this streamline, then the summation of all these three heads will remain constant. There also they can be also expressed in such a form that they represent energy. Basically, this is energy equation I told. So, they can be represented as energy. Let us say G I replace from every term. So, what we get? V1 square by 2. So, this is the kinetic energy associated with the unit mass of fluid. Okay. So, it represents the kinetic energy. Then Gz1, that represents the potential energy of the fluid with respect to a datum plane, and P1 by rho, or P1 into 1 by rho. 1 by rho is nothing but the specific volume. So, PV basically. So, what is PV? We have done it earlier, that is flow energy or flow work. So, flow energy. So, basically somebody calls it loosely pressure energy, but there is no term like pressure energy. Okay. So, this is the flow energy. So, flow energy, kinetic energy and potential energy. So, summation of these three are constant along a streamline. So, along a streamline what can happen? Along a streamline only interchange or transformation between these three forms of energy can occur. Okay. But whatever transformation may occur, the summation of these three forms, that will remain constant. Sometimes this equation is also called mechanical energy equation for the fluid. This Bernoulli equation is the mechanical energy equation of the fluid. Sometimes it is called like that, because here you see that no electrical or chemical energies are there, even thermal energy is also not present. So, this is sometimes called the mechanical energy of the fluid. Well, now I will go to extending the scope of Bernoulli equation. See, Bernoulli equation is for steady, quickly let me write it, then for incompressible, then for frictionless, and then for flow along a streamline. Well, now we can relax almost all the assumption, and we can have modified form of Bernoulli equation, but I will not do that. I will concentrate mainly on the last two conditions. Flow along a streamline, let us see that. Flow along a streamline, well, it is very easy to say that, but thing is that I want to apply Bernoulli equation for practical problem, and practically when there is a flow, it is very difficult to identify this streamline. What is this streamline? See, if I have to apply Bernoulli equation along a streamline, first I have to identify the streamline. So, that becomes almost impossible. So, actually it is like this, that generally we will assume, suppose there is a pipe flow, we will assume that the flow is streamlined, there are streamlined. So, we can apply between 2 points. Now, it can be proved mathematically that if the flow is irrotational, again one may ask question what is irrotational, and if I have to discuss that, we have to do slightly more of fluid mechanics, which this course does not permit. So, if the flow is irrotational, then irrespective of the streamline, we can apply the Bernoulli equation between any 2 points of the flow field. I can give one example. See, if there is a duct like this, in the duct there is a sudden sudden expansion in area, sudden enlargement in the area. So, we will find at the inlet the fluid motion can be denoted by this streamline, but when it goes like this, so here there will be eddies. So, here the flow is not irrotational. Okay. Here we cannot assume the flow to be irrotational. So, definitely if we want to apply Bernoulli equation between these 2 points, we will be at fault. But in general, when there is a straight duct or when there is a very gradual increase or decrease in velocity, in these cases we can assume the flow to be irrotational and apply Bernoulli equation between any 2 points. So, then this flow along the streamline is not a very stringent requirement always. So, we can identify the flows where it is along, where the flow is irrotational, large number of cases almost irrotational, and we can apply Bernoulli equation between any 2 points of the flow field. That gives us certain advantage. Then frictionless. We know all the fluid will have viscosity, whatever small or large it may be, there will be effect of friction. So, then obviously Bernoulli equation, how it can be valid. So, due to friction, what happens? There will be some dissipation of energy. Dissipation of energy means some energy will be converted into form which cannot be recovered back either in the form of flow energy or in the form of kinetic energy or in the form of potential energy. Now, if we can account for this loss, then again we can write down the Bernoulli equation. So, Bernoulli equation can be applicable for certain type of flow where frictional losses are there by adding a loss term. We can write P1 by rho g plus V1 square by 2g plus Z1, that is equal to P2 by rho g plus V2 square by 2g plus Z2 plus HL. HL is the loss. All right. So, this is the correction which we can make to take care of the frictional loss. Now, I will come next how to determine HL, but before that I just like to give some sort of a caution that how we can where we should not apply Bernoulli equation and what type of watch we should make before applying Bernoulli equation. Bernoulli equation is either valid either along a streamline or on some sort of a flow field where the flow is irrotational. all right. Now, thing is that let us say we have got a situation like this. This is a fluid machine. Let us say this is a centrifugal pump. The flow is entering like this and fluid is going out like this. So, outlet, let us say we are giving 0.2 and inlet we are giving as 0.1. Can we write down Bernoulli equation between 0.1 and 0.2? The answer is no, because there is some sort of energy input. If there is energy input, let us say there was a streamline, along this streamline we had some sort of energy which is constant mechanical energy. As soon as this energy input is there, okay, streamlines we will get with some other energy constant. So, obviously, we cannot write the summation of flow energy, kinetic energy and potential energy here is equal to the summation of flow energy, kinetic energy and potential energy at the outlet of the machine. So, in a nutshell, whenever there is a machine, whenever there is mechanical energy input, so we cannot write down Bernoulli equation taking a point upstream of that and downstream of that. We cannot do it. When there is heat input, then also we cannot do it taking 2 points upstream and downstream of the heat input. Okay. When there is large deviation from irrotational flow, just like I have told that it is a sudden expansion kind of a thing. So, there also we cannot write down Bernoulli equation. Let us say we have got a pipeline and branching of pipeline, something like this. So, if we have to apply Bernoulli equation between these 2 points, we have to be careful, because here the continuity equation is not valid. The mass flow rate here and mass flow rate here, they are not the same. It can be done, but with some sort of a caution one has to do it. Okay. So, these are the situations where we should be careful in applying Bernoulli equation. So, I will stop here today, but I will elaborate on HL, that is the main part of this lecture, in the next class.